Okay, so we talked about some things in chapter 27 as far as circuits. We talked about what current is, Ohm's law, and actually let me bring up my screen here, or my whiteboard. And so we're going to talk about a little bit more detail. How do we analyze a circuit? And so this is what we have from last time that's going to be carry over from what we discussed. So we talked about Ohm's law, right? Really important in this chapter. Okay, and in Ohm's law, we said that the voltage across some resistor, VR, equals the current times resistance. Okay, so Ohm's law becomes really important in this. We use it fairly often. We also talk about capacitance a little while back. I think that was actually in chapter, I want to say 26. But we talk about capacitance as charge over voltage. Okay, Ohm's law and capacitance, and a couple other things. So the other laws that we talked about, or the other important concepts that we talked about in chapter 27 were, I always forget how to spell, I think it's two H's, Kirchhoff's laws. So Kirchhoff said that voltage around a loop in your circuit always equals 0. Just say total voltage, or the sum of the voltages. Okay, so that's one, and then the other one, so that's called the loop law. The other one is the junction law. So junction law says current, let me see, total current entering a junction, or anywhere in the circuit really. Total current entering a wire, a junction, doesn't matter. Entering a junction equals the current leaving the junction. So let me draw a circuit diagram to show you these two kind of in action here. Okay, so like a simple circuit diagram will be something like this. You have, like, say, a battery. Okay, so remember we said in a battery, the longer side is a positive end, right? It's the side with higher voltage. The shorter side on the bottom there is your negative end, right? The side with lower voltage. The longer side has higher voltage, shorter side has lower voltage. And we usually say that lower voltage side is 0. It doesn't have to be, but we usually say that. And we have, let's say, a circuit like this. Put a resistor here. Resistor here. Okay, and there's our circuit. What kind of circuit is that? Are those resistors series or parallel? You guys remember? We're going to talk more about it today, but we talked about series and parallel before. Yeah, that's parallel. Good job. So this is, I'm going to call this R1, R2. Okay, so let me apply these two laws that we talked about. So the first one is a loop law. Loop law says that if you go in a path, and we're going to talk about this more in detail today because I just introduced it last time. If you go in the path, that total voltage is going to equal 0. So the sum of your voltage is going to equal 0. So we have two voltages here. We have the voltage of the battery, right? As you go on the left side of that path there, that's going to be the voltage battery. As you go around that circuit now, going, would that be clockwise? Going clockwise, and then through voltage of the resistor, well, that voltage of the resistor is going to cause a voltage drop. Okay, so that's going to be a minus VR. And that's going to equal 0. Okay, which tells us something, right? So that in itself, what I just wrote, is Kirchhoff's I think I'm saying that wrong, Kirchhoff's loop law, right? And from that, we can see that your voltage of your battery equals the voltage of your resistor. Okay, so we're able to use that equation that I got from the loop law to say that the voltage of battery is voltage equals the voltage of resistor, which you should be able to tell anyway because they're in parallel. So one of the characteristics we talked about, and we'll talk about again today, that if you have circuit elements in parallel to each other, they're going to have the same voltage. All right, and the other one, the other law that we discussed here is that current one. So we have total current going this way. All right, and here's the junction. Well, at this junction, that current's going to split up. You have current going to the right, call that I2. Current going down to the left, or going down, call that I1. Okay, so what the junction law says is that current, the total current entering in that junction equals the current leaving that junction. So that's I equals I1 plus I2. Okay. Good. All right. So that's kind of just a review of what we talked about in the previous chapters. We're going to use those concepts today because now we're going to look at circuits more in detail and see what how we can use it to find current, to find voltage, to find different things, to observe different circuits and see their behavior. Okay, so that's where we're headed. Okay, so I like to start this chapter with simple circuits, and then I start to increase the difficulty as we go. So let's look at a simple circuit here. Okay, so let me. Okay, so here's my simple circuit that we're going to start off with. We're going to start off with a battery. I'll do it black. Battery. I'm going to go to a switch. And then from that switch, we're going to go to a capacitor. Okay, so okay, let me label these as my capacitor. This is my battery with some EMF. And that thing up here, that's my switch. So when the switch is open, as you can see, which it is right now, I have no current running through it. Okay. So we're gonna, once I close this switch, put that in a different color. Once I close the switch, so I'm gonna bring the switch down and close it. Once I close the switch, that's when current starts to flow, right? So current will start to flow here on this side. Current goes here. Okay. Okay, so we're gonna once we close the switch, current starts to flow, and as the current starts to flow here, we start to get build up in the capacitor. Okay, so let me put that here. Switch when switch is closed. Okay, the capacitor begins to build charge. Okay, so what's going to happen here is that we're going to start to get a lot of positives on this side. Okay, all these positives on the top part, and on the bottom, we're going to start to get all these negatives here. Okay, so that capacitor starts to build up. Now remember, capacitance tells us how much charge it could hold at a specific voltage. Okay, that's what C equals Q over V. Okay, so how much charge it could hold at a specific voltage. So what's going to happen is that this will start to build up charge. Eventually, because this is in parallel, right? This capacitor here is in parallel with the battery, right? Eventually, these are going to have the same voltage. Okay. Okay. So let me add that into my note here. So voltage of the capacitance begins to increase. The capacitor. Okay. Eventually, let me put eventually reaching the same voltage as the battery. Okay, so how do I know it's going to reach the same voltage as the battery? Well, if we do the loop law, right, which we mentioned earlier, here's my loop. Wait, I want a different color. Okay, so if I go counterclockwise around this battery, and let me start here at the bottom corner there. If I go counterclockwise and I add all my voltages, well, I have my voltage from my battery, and then if I look at the capacitor, I'm going from the positive side of the capacitor to the negative side, right? If I'm looking at that loop, going in that counterclockwise direction, if I'm going in the counterclockwise direction, going from positive to negative, we have to ask the question, is that an increase in voltage? Is my voltage going up or is my voltage going down? Okay, so if we're going from the positive side of the capacitor to the negative side of the capacitor, that is a decrease in voltage there. Okay, so there's going to be a minus voltage from the capacitor. Right, and that completes my loop. Okay, and if that completes my loop, the loop law says that all the voltage around your whole loop equals 0. So this is proving what I wrote there on the side, that this eventually becomes VC. The voltage of the capacitor is eventually going to equal the voltage of the battery. Okay. All right, so let me see here. I don't know why this changed colors. Okay. So once the capacitor reaches its voltage, in other words, reaches its maximum charge for that voltage, charge for that at that voltage, current will stop. Well, we'll go to 0. Okay, so once that capacitor reaches its maximum amount that it could hold, you can't have any more current, because that current is going to try to put more charge in the capacitor. You know, if I could personify it for a second, the capacitor is saying to the circuit, like, hey, I can't take any more charge, so you're going to have to stop this. So the current goes to 0 once the capacitor reaches its maximum amount of charge that it could hold. Okay. So simple circuit here, but even I mean, we just have a battery, a switch, and a capacitor. But even in that simple circuit, you know, a lot is going on as far as what's charging, what happens to currents, and all that. Okay. All right. So another simple circuit here, which I'll try to fit on the bottom of your screen. This time we won't put a switch. Okay, so here we have this battery. If you forget what the E is for, the E represents the EMF. EMF is essentially the voltage of the battery, right? Ignoring any internal resistance. Okay, so this battery has an EMF, a voltage, and I connect it to the resistor. Okay, now resistor is going to act a little differently than the capacitor, right? The resistor does not store charge. You can think of it as impedes charge, because as we saw last week in chapter 27, when you have those charges flowing through the wire, you have the atoms there, and as those charges hit those atoms, it slows it down, right? And that's what slows the, when we're talking about drift velocity, is those collisions. Okay, so resistance is not storing charge, but it's responsible for all those collisions going on. So in other words, it's not going to stop the charge completely. It might weaken it or might lessen the currents, because more resistance gives you less current, but it's not going to stop it like the capacitor did. So what we're going to have here, once we connect it, you still have current going through here, and that current will continue. So a little different than the capacitor. Okay, so here, current will continue through the circuit, or through the resistor. Okay, it'll just keep going. Now, of course, I'm not taking into account like things like corrosion or anything like that, or temperature. Temperature would affect the current as well. So I'm not considering that. So given a perfect circuit, this current would just keep going. Of course, things like corrosion in the battery would eventually stop that current. Okay, so that will continue to the resistor indefinitely for a perfect circuit. And how much current flow the circuit is given by Ohm's law. Okay, so Ohm's law, if you solve for current using Ohm's law, I equals voltage over R. Yeah, that's just using Ohm's law, right? V equals IR. I just solved for I there. Okay, so what's that telling me is that if I increase my voltage, which in this case, I mean, if you're getting confused with the symbols there, okay, I understand that. The voltage I'm talking about is the voltage from the battery, so the EMF from the battery. Okay, so if I wanted more current going through my circuit, then I could do two things. I could increase the voltage going through the battery, right, which would increase current, or I could decrease resistance through my resistor. Right. So pretty simple circuit there. There's not much more to talk about in that circuit. I guess the only thing I could say here is that because often in examples or homework problems, or even that group work that I talked about that you guys are going to be doing called Crack the Circuit, a light bulb is acting as a resistor as well. So you might see something like this. It's going to look a little different. It's just going to have like a circle around it, and instead of, it's going to be kind of curled. Okay, well, that's essentially the light bulb acts as a resistor. So there's not that much difference between a light bulb and resistor. In reality, though, that light bulb heats up, and then the resistance is going to change as a function of temperature. Okay, so those are my two simple circuits that we start out with. Let's increase the difficulty. A little harder circuit this time. We're going to now include two batteries and two resistors in the same circuit. Let me see here. So let me draw this out. Okay, so a little harder here. This is going to be a 9-volt battery on this side. The right side is going to be 6 volts. The top, I'm going to call this R1, and R1 is 4 ohms. And on the bottom here, call that R2, and that is 2 ohms. Okay. So there's a couple things. Oh, okay, so what do we want to do with this circuit? I want to find the current and voltage across each resistor. Okay, so that's what I want to do in the circuit. All right, so a couple things we could just look at this and know. So first of all, there is no junctions here, right? If you look at the circuit, nothing is splitting up. As you go around this circuit, it's just one constant loop, no junctions. What that means, if there's no junctions, is that we're going to have the same current throughout the whole loop. Okay, so let me include that here. Do that a different color. So no current. Oh, sorry, no junctions means same current throughout circuit. Okay, so I get that from the junction rule. If no matter where you look at, it's always going to be the same current going in as the same current coming out because there are no junctions. Okay, and that's pretty much true for anything in series, right? We always have series connections. Series connections gives you the same current. All right, now another thing I could look at this and determine is the direction of currents. Although this is not super necessary because if you didn't know, if you picked the wrong direction of current, your math will correct that for you later on by giving you a negative number at the end, okay, when you do your calculations. But we could look at this and get an idea without doing any kinds of calculations, because if you look at the batteries, I think I said in class, maybe I didn't, or a previous lecture, that you can think of batteries as pumps. They're pumping in these charges, this current, into the circuit. You have a 6-volt pump on the left side and a 9-volt pump on the right side. Okay, and they're both kind of pushing against each other, right? The positive, let me go here. The positive on this end is wants to put current this way. The positive on the 9-volt battery wants to go this way. So the 9-volt being a higher voltage, or in my analogy, a stronger pump, is going to put current this way, and it's going to overwhelm the current coming from the 6 volts. Okay, so it's just simply by the fact that this has a higher voltage means that current is going to be leaving this battery here. Okay, so that is the direction of my current. Like I said, if you didn't see that and you started your calculations anyway, your math would correct you. At the end of your calculations, when you calculate current, you get a negative number for current. That means that negative number means that you picked the wrong direction of current. So it just means you got to flip your direction for current. All right. So so those are the couple things that we could get just by looking at this. The rest of it, to go any further, we have to analyze the circuit a little bit more using the loop rule. Okay, so let's use the loop rule. I'm going to pick a loop, and I do like to pick my loops going the same direction as current. So let's say I start here, and my loop is going to go this way. In that counterclockwise direction. Okay, so remember the loop law. Loop law says that the sum of your voltages around this loop. So you're going to add up all the voltages in this loop equals 0. Okay, so I have my starting point. My initial point, I'm going to say is right here. So I'm going to start there at that dot and go in a, what would that be, counterclockwise direction and add all my voltages. Okay. So if I go in a counterclockwise direction, I'm going to hit that battery, right? So and the direction of the loop really does matter. So looking at the battery, I start from right here from a lower voltage, right? Remember, that's what the short line means, a lower voltage, and goes up to a higher voltage. Okay, so that is a voltage increase right there, right? I'm increasing my voltage by going from the short side to the long side. So I'll write this as an increase in voltage by 9 volts. So I have a 9-volt increase. I'll put a positive here. Then as I go around, I keep going around the circuit. So I did my battery, go around here, and I go to the resistor. Well, in this case, as I go to this resistor in this direction, that resistor is going to give me a voltage drop. Okay, so there's a couple of reasons why it's a voltage drop. I think actually, I guess only one reason. Current always goes in the direction of decreasing voltage. So if current is going this way, right, through the resistor, then that means as I go to that resistor, voltage is decreasing. So let me put that here as a negative voltage drop across resistor 1. Okay, so voltage drops as I go to resistor 1. Let's keep going. Now I get to this battery. This battery, now again, direction matters, right? How you're going to this battery matters. It starts from a large voltage, right, a higher voltage, and goes to a shorter voltage. So voltage drop or voltage gain? Yeah, okay, voltage drop. So just be careful there. Yep, just be careful there, because here's a mistake that happens a lot when I'm grading papers. I see that a student sees a battery. Great, you see a battery. I don't want you guys to think that just because you see a battery means that your voltage is always going to be positive, right? It depends on the direction of your loop. That's what makes it a positive voltage or a negative voltage. Because we're going in that counterclockwise direction, we're going from that higher voltage to that shorter voltage. So we would need to write this as a -6 volts. Okay, so just be careful with that. Don't assume that because you have a battery there, you're always giving a voltage gain. It really does depend on the polarity of that battery. All right, so we get the battery, voltage drop, and then we go to resistor. And as we're going across the resistor here, okay, like this, in that direction, as we go across the resistor, that we're going the same direction as current. Remember, current keeps up that same direction. I could draw it a couple of times here. Okay, this is my current. Okay, current always goes from a higher voltage to lower voltage. So we're looking at that resistor. That resistor and that going in that counterclockwise direction is going to give me another voltage drop. So I'm going to put this here as a minus VR2. So there you go. I did my whole loop, and as I go across that whole loop, I know the total voltage equals 0. Okay, so where do we go from here? We're trying to find current and voltage across each resistor. Well, I'm going to I could do a couple things, I guess. I could combine the 9 and the -6, right? And the rest of it is algebra. Once you get that, I think the physics is pretty much done. The rest is just doing the algebra. So 9 and 6 there, you get 9 minus 6, you get 3 volts. And then for this VR1, well, if I use Ohm's law, IR, I could just plug in I times R1 minus I times R2, right? I'm plugging in for my VR1 and my VR2. And of course, I have numbers for those, right? R1 is 4, R2 is 2. So I'll work out the rest. So 3 volts minus I times 4 minus I times 2 equals 0. And so we could solve for I with that, right? So we get, double check my math here. I'm kind of just doing it in my head, but I get I equals 0. Let's say I didn't put my sig figs here. Let's say it's accurate at 2 sig figs. Okay, that's my current. Okay, so we found the magnitude of current being 0.5 amps, and that is because, like we said earlier, there's no junctions. That 0.5 amps is going through resistor 1 and resistor 2. So both have the same current. All right, so now we just have to find the voltage across resistor 1 and voltage across resistor 2, which is not too hard. We just use Ohm's law. So voltage across resistor 1 equals IR, 0.50 amps, times the resistor of R1. So there you go. We get 2.0 volts. And same thing for voltage across resistor 2. For resistor 2, IR, right, that's my Ohm's law, current times resistance, 0.50 amps times my resistance, which is 2, equals 1.0 volts. Okay, so if you're ever unsure whether you did that correctly, plug it back into your equation here, right, your loop law. If you plug those voltages back into your loop law, you should get 0 once you plug in your voltages. And I think we do get, right, 9 minus 2 minus 6 minus 1. Yeah, all those, that does indeed give you 0 here. Okay. All right, so a little bit harder because now we have I put 2 batteries and 2 resistors, but that loop law really comes in handy as far as finding the current there. All right, so we'll take a break here, and when we come back, I have I have another circuit here that's even harder. So we're gonna increase the difficulty here and see how we do that.